Welcome back. So in last part we discussed the we have started the Bohr's model. We have discussed already 3 points. These are the continuation from Rutherford model. Now in this part we will start the postulate of the Bohr's model. So this is also called, let me write it, Bohr's quantum postulate, right? There are 3 postulates. First one, electrons inside an atom, these are very important, so we have to remind it always to recall it. Atom can only revolve in some allowed orbits. When an electron revolves in an allowed orbit, it does not radiate any kind of energy. Okay, means that in Rutherford model, from Rutherford model we know that the electrons are circulating around the nucleus and that path is called orbit. There are various orbits, okay. But what was the problem in Rutherford model? According to electromagnetic theory, when a charged species circulating follow a rotating path, then what happens? It should emit electromagnetic radiation, which essentially decrease the energy of that particle. Okay, but Bohr considered that when an electron revolves in an allowed orbit, in all orbit are not allowed. That means any radius we can't consider as orbit. So there are some fixed orbit. That means there are some fixed radius in which electrons can rotate or revolve around the nucleus. That's are called the allowed orbit. When electrons are revolving in those allowed orbit, electron does not radiate any kind of energy. If electron does not radiate any kind of energy, then the energy of the electron would not decrease. That's why those orbits are called the stable orbit or the stationary orbit. Correct? This is the case. So clearly it against the Maxwell laws of electromagnetism, which says that it should radiate energy, but Bohr considered that, Bohr postulated that no, when electrons are revolving in an orbit, the allowed orbit, it will not emit any kind of radiation. So this is the criteria of the stationary orbit. Okay. Now the second one. What was the second postulate? We have to understand each postulate very well. Transition of electron from one stable or stationary orbit to another, that is possible. Transition between two stationary orbits is possible, and during transitions an emission or absorption of radiation occurs. Okay, while rotating in an orbit, no radiation will occur according to Bohr postulate. But when one electron is making transition from one orbit to another orbit, it may be excitation, it may be de-excitation. In that case, absorption or emission of radiation would occur. That is the case. and also the frequency of the radiation, let us say the new frequency of the radiation would be daily divided by h cross, no h, this is the frequency of the transition. Okay, where we know these things, right? This h is the Planck constant. As I mentioned before, at that time when Bohr is giving these postulates, the Planck constant was known to all actually. That means Planck's black body radiation was known. Planck gives the justification of the black body radiation by using the discreteness of the light. That's why the h is known to all. This is called the Planck's constant. The value is 6.26 10 to the power minus 34 joule second. Okay, so this is the our frequency, right? So let's say, let's consider this is the nucleus, this is one orbit and this is another orbit, right? There are two orbits. So electron was there, now it jumps to here, another orbit. This is, let's say, energy of in this orbit is E1, here E2. So to jump from one orbit to another orbit, it must absorb some kind of energy, because this is excitation, because the energy is increasing, means E1, say E2 is greater than E1. So in that case, it must require some external energy, that is the excitation energy. If we provide that excitation energy, then the electron will excited to the E2, from E1 to E2. So clearly the daily would be E2 minus E1, correct? Yes, so it should be equals to h nu. So for this excitation we should provide energy, provide the frequency nu, which should be equals to E2 minus E1 divided by h. So we know these things from Planck's idea. If it is other way around, then also if it is de-excitation, let's say from here to here, then the daily will be same. Daily is the difference between the energy. These things will be, equation will be same, but in that case this energy will be emitted from the atom, because de-excitation is occurring, right? From higher excited state to lower excited state, the energy is decreasing. So extra energy will be emitted from the atom. So there are two cases, one is emission, the second one, and this is the emission, this is the absorption, right? So there are two cases. In those cases, the radiation can absorption or emission, here the radiation will be absorbed, here radiation will be emitted. Okay, so this is the case. So and this is called, let me write it, this is called Bohr's frequency conditions. So this is the second postulate, right? Now the third one, most important postulate, we can say, the orbit. We have already stated in the first postulate that there are some specific orbit, there are some any radius is not allowed. Okay, there will be some special radius in which electron can circulate, revolve around the nucleus, and those paths is called the orbit or stationary orbit, in which the energy of the electron will not change, it will not radiate any kind of radiation, any kind of electromagnetic wave. But how we will know that which radius will be allowed? Okay, means around nucleus this may be a stationary orbit, but this may be also, this may be also. Which orbits will be stationary orbit? That means which radius are allowed to give us the stationary orbit, that we have to know. Both give the justification, give the answer in the third postulate, the orbit where the angular momentum okay of the electron is an integral multiple of h by 2 pi is known as stable or stationary orbit. So this is totally ad hoc thing, right? How Bohr knows this? Actually, Bohr did the back calculation, okay? Because in that case, there are some experimental result, okay? And atomic spectra, there are some Rydberg constant. These experimental results were known to scientists, and scientists were trying to prove those results from some theoretical model. So Bohr did some kind of back calculation, we can say, and find out that if there are some fixed orbit, allowed orbit, that's called the stable orbit, and in those orbit the angular momentum of the electron should be integral multiple of the h by 2 pi, then only we can prove at the in the ultimate case we can prove that ultimately atomic spectra, Rydberg constant, these experimental results will be justified if we consider this thing. Otherwise, these things will not be, the experimental results will not be theoretically justified. So for giving the theoretical justification, Bohr considered this ad hocly. You can say that there is no theoretical justification behind these postulates. That's why it's called postulates, because you can't question postulates. Why? Okay, so that's why Bohr considered this. But after some year, when the quantum mechanics developed a little bit after de Broglie hypothesis, from de Broglie hypothesis we can give the theoretical justification behind these postulates. Okay, we will come into that later, but for now this is the thing. Okay, this is the postulate. So what is the angular momentum? We know that for circular motion, angular momentum L is I omega. I is the moment of inertia, omega is the angular velocity. Okay, so I is mr square. So mr square omega. So we can write it mvr. V is the velocity, not the angular velocity, linear velocity, right? This is the angular momentum. Okay, so this is mvr. So Bohr says that if mvr equals to some integral multiple of h by 2 pi, let's say n. Integral multiple means n should be integer, right? N should be 1, 2, 3, these things. Integral, this means integral multiple. Then this radius will be allowed. Then electron can revolve in this radius, and those paths will be considered as a stable orbit. So we can write it, we should give the suffix Vn and Rn. Otherwise, if let's say this is 1, if n is 1, then the R and V will be different. If n is 2, then R and V will be different, right? So R and V is not the fixed, that depends on the radius. We know that from circular motion, we know that if this is the orbit, then R is different clearly and V will also different, because ultimately we have to balance the centrifugal and centripetal force, right? So if R is changing, then also V should change, otherwise those balance will not be there. So V and R, velocity and the radius, is clearly function of the orbit. Radius is indeed, we can see from the picture even, but velocity is also function of the orbit. If we change the orbit, then the velocity also change. That's why we add the suffix, it depends on the value of n. So this is the mathematical form of the third postulate, right? So it also written as like nh cross. We know, right, h cross is equal to h by 2 pi. So mvr equals to mv and rn is equal to nh cross. Okay, so this is called Bohr's quantum conditions. Okay, and n is called principal quantum number. okay, of electron or orbit, we can say this. So these radius are allowed, and these radius are called Bohr radius. The stable radius are called, these radius are allowed, which follows this equation. Those radius only allowed in which the electron can revolve, and these are called the Bohr orbit. Let me write it. This is a Bohr orbit, right? So now we can give some justification of this finding, this postulate from the de Broglie hypothesis, right? What is that? We know the matter wave from de Broglie hypothesis, as we discussed the de Broglie hypothesis in previous chapter. That's why I am saying this. Let's say, as electron is not a particle actually. If we, when the quantum mechanics evolve much later, we know these things, right? There is some matter wave, means dual nature of any particle, or any particle or the light is there. That means radiation also has some particle nature, particle has also some radiation like nature. So these are the dual nature. So electron is not a pure particle, it's actually a wave particle duality is there, right? So it's called the matter wave. So if we consider electron as a matter wave, and this is some orbit, let's say, and if electron is matter wave, then it should be like this. There should be some, let me draw it properly. This should be standing wave, otherwise there will be decoherence, and what happens, the overall wave will not be stable. We are considering orbit, that means in those orbit electron must be stable and it should rotate around the nucleus. So we are considering the stable orbits. So in stable orbit electron must be stable, so that means it should be form a standing wave, okay, like this. So to form the standing wave, what should be the condition? The condition must be like this. The circumference is 2 pi r, right? Let's say it's the Rn. For time being, it's 2 pi r. It should be equals to n lambda. This is the wavelength. This is the lambda, right? We know this is the wavelength lambda. So to form a standing wave, there must be integral number of lambda. Here the 4 is there. If there is 2.5 or 3.5 something, then what happens? Phases will be cancel each other, and after all the total wave, the matter wave, will not be stable, it will be vanished, okay, due to the cancellation of the phases. So we can say that we know from these things, from the standing wave part. So this must be, n must be integral, that means n should be 1, 2, 3 like this. If it is 0, that means there is no electron, so 0 is not considered, that's why. So from here we can say that lambda should be 2 pi r divided by n, right? If it is lambda is 2 pi r divided by n, then from de Broglie hypothesis we know that lambda should be h by mv. So if it is h by mv, then we can say that mvr equals to nh by 2 pi. It's straightforward. Or for make it general, we add some fix mvrn equals to nh by 2 pi. So this is some we can say it's not the pure derivation of the Bohr's quantum condition. This is not the pure derivation. We can give the justification in a if we want to give some justification, simple justification, then this will be like this. From de Broglie hypothesis we can prove this, okay. So true explanation we can also give from quantum mechanics. We will not get into that, but this is just oversimplified justification, but this also gives the correct result. So in this part, let me stop here. We discussed the Bohr postulate totally. 3 postulates are there. So we discussed the 3 postulates, and also we discussed the some theoretical basis of the 3rd postulate, Bohr's quantum condition. In next part, we will discuss the application of the Bohr's theory. So let me stop here. We will continue from here in next part. Thank you.